What if I told you that right now, at this very moment, humanity has already designed a method to reach another star system in just 20 years? Not thousands of years, not centuries, 20 years. And the truly insane part? The spacecraft wouldn't have engines. It wouldn't carry fuel. In fact, it would be so small you could hold it in your hand, yet it would travel at 20% the speed of light. That's 134 million miles per hour. This isn't science fiction. This is Project Starshot, and it's the most audacious, brilliant, and absolutely bonkers plan humanity has ever conceived for leaving our cosmic neighborhood. But here's what will completely shatter everything you think you know about space travel. The real breakthrough isn't the technology. It's that we finally understood we've been thinking about interstellar travel completely backwards for the past 100 years. For decades, we've been trying to make our spacecraft bigger, more powerful, carrying more fuel. We've been thinking like we're still in the age of ocean liners crossing the Atlantic. But physicist Philip Lubin at UC Santa Barbara had a revelation in 2016 that changed everything. What if we stopped thinking about spacecraft like ships and started thinking about them like particles? What if, instead of one massive vessel crawling through space, we sent thousands of tiny probes, each the size of a microchip, riding on beams of light itself? This is the idea that has serious scientists, billionaires like Yuri Milner and Mark Zuckerberg, and even the late Stephen Hawking betting $100 million on. And when you understand the physics behind it, when you see how elegantly it solves problems that have stumped humanity for generations, you'll realize we're standing at the edge of becoming an interstellar species. Not someday, not in some distant future, in our lifetimes. But before I blow your mind with how this actually works, do me a favor, hit that like button right now, and smash that subscribe button, because over the next 3.5 hours, I'm going to take you on a journey that will fundamentally change how you see humanity's place in the cosmos. And I want to know, drop a comment right now telling me what country you're watching from and what time it is where you are. I love seeing this global community come together to explore the universe. Now, let's talk about why every method we've tried before this was basically doomed from the start. To understand why Project Starshot is so revolutionary, you first need to understand what physicists call the tyranny of the rocket equation. And trust me, once you see this, you'll realize why getting to another star seemed impossible for so long. Here's the brutal truth about rockets. To go faster, you need more fuel. But more fuel means more weight. More weight means you need even more fuel to move that weight, which means more weight, which means more fuel. You see the problem? It's a vicious cycle that the Russian scientist Konstantin Tsiolkovsky first mathematically described way back in 1897. His equation showed that the amount of fuel you need grows exponentially, not linearly, with your desired speed. Think of it like this. Imagine you're trying to run a marathon, but for every water bottle you want to carry, you have to also carry the backpack to hold it, plus extra food to fuel the weight of carrying that backpack, plus a bigger backpack to carry that food, and so on. Eventually, you'd be carrying so much stuff that you couldn't even take a single step. That's exactly what happens with rockets trying to reach interstellar speeds. The nearest star system to us, Alpha Centauri, is 4.37 light-years away. That's about 25 trillion miles. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour. Sounds fast, right? At that speed, it would still take over 6,700 years to reach Alpha Centauri. Our entire recorded human history is only about 5,000 years old. We're talking about a journey longer than all of human civilization. But wait, it gets worse. What if we tried to speed up? What if we wanted to get there in, say, 100 years instead of thousands? Using conventional rockets, you'd need so much fuel that the spacecraft would have to be bigger than the entire planet Earth. I'm not exaggerating. Engineers had done the math. A rocket-based spacecraft that could reach even 10% the speed of light using chemical propulsion would require more mass than exists in our solar system. This is the wall we've been hitting for a century. Scientists have proposed all sorts of wild solutions. Nuclear pulse propulsion, literally detonating thousands of atomic bombs behind your spacecraft to push it forward. Freeman Dyson worked on this in the 1960s with Project Orion. It could theoretically reach 10% light speed, but you'd need thousands of nuclear warheads, and the spacecraft would have to survive hundreds of nuclear explosions right behind it. Plus, there's the tiny problem of the Nuclear Test Ban Treaty. Then there's antimatter propulsion. When matter and antimatter collide, they annihilate each other in a burst of pure energy, the most efficient energy source in the universe. The problem? We can only produce antimatter in tiny amounts in particle accelerators, and it costs about $62.5 trillion per gram. To fuel an antimatter rocket to Alpha Centauri, you'd need several tons of the stuff. That's more money than exists in the entire global economy, multiplied by millions. What about ion drives? They're more efficient than chemical rockets and already used on some satellites. But they produce thrust, measured in the equivalent of the weight of a few sheets of paper. To accelerate a conventional spacecraft to interstellar speeds with an ion drive would take centuries of constant acceleration, and you'd still need a power source bigger than anything we can build. Generation ships? Massive vessels where generations of humans would live and die during the journey? The engineering challenges are mind-boggling. You'd need a completely closed ecological system that could sustain itself for thousands of years, perfect recycling of all resources, and somehow you'd have to deal with the social and psychological impact of people being born, living, and dying on a spacecraft, never seeing their destination. It's theoretically possible, but we're talking about a project that would cost more than the GDP of every nation on Earth combined. Here's where it gets really crazy. Even if we solve the propulsion problem, there's another nightmare waiting for us: dust. In interstellar space, there are tiny particles floating around. At the speeds we're talking about, even a grain of sand becomes a bullet. A spacecraft traveling at 20% light speed, hitting a dust particle the size of a pea, would experience an impact with the force of a small nuclear weapon. You'd need shielding so thick and heavy that you're back to the rocket equation problem again. For decades, this is where we were stuck. Every solution created new problems. Every workaround hit fundamental physical limits. Interstellar travel seemed like a dream that violated the laws of physics and economics. And then Philip Lubin asked a simple question. What if we're thinking about this completely wrong? What if the spacecraft didn't need to carry its own propulsion at all? What if we just pushed it from Earth? This is where everything changes. This is where the insane becomes possible. But to understand how, we need to talk about something you probably learned about in high school and never thought about again: the photoelectric effect. Trust me, this is going to blow your mind. In 1905, Albert Einstein published 4 papers that revolutionized physics. Everyone knows about E=mc and relativity. But the paper that actually won him the Nobel Prize was about something much simpler: light pushing things. Here's the discovery that changed everything. Light isn't just waves of energy. Light is also made of particles called photons. And here's the kicker: even though photons have no mass, they carry momentum. That means when photons hit something, they actually push it. Not much, but they push it. You've actually experienced this force yourself. You just didn't realize it. When sunlight hits your skin, you're feeling the warmth from the energy, but you're also being pushed infinitesimally by the momentum of trillions of photons. The pressure is incredibly tiny. Sunlight at Earth's distance produces about 9 micronewtons of force per square meter. That's like balancing a single grain of sand on your hand. Basically nothing. But here's what will blow your mind. In the vacuum of space, there's no air resistance, no friction. That means even a tiny force, applied continuously, will keep accelerating an object, forever. It never stops speeding up. A grain of sand's worth of pressure, applied for years, can eventually push something to incredible speeds. This effect was actually discovered by accident by early satellites. Engineers noticed their satellites were being pushed slightly off course by sunlight pressure. They had to design their orbits to account for it. Nature already uses this principle. Comet tails always point away from the sun because solar radiation is literally pushing the dust and gas away. In the 1970s, scientists started seriously thinking, could we use this? Could we build giant solar sails that would catch sunlight like a sailboat catches wind? The Soviet Union actually tested this in the 1990s with the Znamya project, a 20-meter mirror in orbit that reflected sunlight. Japan's Icaros probe, launched in 2010, became the first spacecraft to successfully demonstrate solar sail technology in interplanetary space. It worked. It actually sailed on sunlight to Venus. But there's a problem. As you get farther from the sun, sunlight gets weaker. It follows the inverse square law: double your distance, and you get 1/4 the light. By the time you're past Mars, solar sails become basically useless. You can't ride sunlight to the stars, because there's not enough sunlight once you leave the solar system. This is where Philip Lubin's revelation came in. He thought, what if we don't rely on the sun's light? What if we build our own sun? What if we created a laser array so powerful it could push a spacecraft all the way to the stars? Lasers are coherent light, all the photons moving in the same direction, in phase with each other. Unlike sunlight that spreads out in all directions, a laser beam can stay focused over enormous distances. And here's the beautiful part. We could build the laser array on Earth, or in Earth orbit, where we have abundant power. The spacecraft doesn't need to carry anything except a sail to catch the laser light. No fuel, no engines, no propulsion system at all. The numbers are almost unbelievable. Lubin calculated that with current technology, we could build a laser array about 1 kilometer across, roughly the size of a large city block, with a power output of 50 to 100 gigawatts. For context, that's about 50 to 100 nuclear power plants worth of energy. It sounds insane, but here's the thing. We already have lasers that are powerful for industrial applications. We're just talking about scaling up and putting them in one place. This laser would fire at a spacecraft equipped with an ultra-lightweight, highly reflective sail. The spacecraft itself would be tiny, the size of a computer chip, weighing just a few grams. Why so small? Because of Newton's second law, force equals mass times acceleration. The smaller your mass, the greater your acceleration from the same force. By making the spacecraft incredibly tiny, the same laser power can accelerate it to mind-bending speeds. The math works out to this. A 50-gigawatt laser array could accelerate a gram-scale spacecraft to 20% the speed of light in about 10 minutes. 20% light speed. That's 134 million miles per hour. At that speed, you'd reach Mars in less than 30 minutes. You'd pass Pluto in about a day. And you'd reach Alpha Centauri in about 20 years. Think about what this means. A probe launched today could send back pictures of another star system while many of us are still alive. Not in some far future. In 2 decades? But here's where it gets even crazier. And this is what convinced Stephen Hawking to back the project. You don't send just one probe. You send thousands, maybe millions. Each one costs about as much as an iPhone to manufacture. They're so small, so light, that you could launch thousands on a single rocket. Each probe is loaded with cameras, sensors, and a tiny chip for processing data. They'd fly through the Alpha Centauri system at 20% light speed, way too fast to stop or orbit. But in the few hours they're passing through, they'd take millions of photographs, gather data on any planets, look for biosignatures, measure radiation levels, map magnetic fields. Then they'd beam that data back to Earth using a tiny laser of their own. Here's the insane part. Even at light speed, The signal takes 4.37 years to reach us. So the total mission time is about 25 years from launch to data return. 1 human generation. We could launch these probes before a child is born and show them pictures of another star system before they graduate college. And because you're sending thousands of probes, redundancy is built in. Some will be destroyed by dust impacts. Some will malfunction, but many will make it. It's like nature's strategy: send millions of seeds, only some need to survive. This approach solves every major problem that's plagued interstellar travel. No fuel needed check. Can reach relativistic speeds check. Affordable with current technology check. Can launch within a decade or 2 check. But there's one question you're probably asking right now. If this is so brilliant, what's the catch? Why haven't we done it yet? Hold that thought. Because the engineering challenges of actually building this system are so mind-bending, so at the edge of what's physically possible, that when you understand them, you'll see why this is truly humanity's most insane idea. And yet, it might actually work. Let's talk about what happens when you try to shoot a laser at something traveling 134 million miles per hour through interstellar space. The challenges are so extreme, they sound like joke problems a physics professor would make up to torture students. Except these are real problems that real engineers are trying to solve right now. Challenge number 1. Aim. You're trying to hit a target the size of a chip, moving at 20% light speed, millions of miles away. How precise does your aim need to be? Avi Loeb, the chairman of the Breakthrough Starshot Committee and Harvard astrophysicist, calculated this. The laser needs to track the spacecraft with an accuracy better than 10 nanometers. That's about the width of a virus. For comparison, the James Webb Space Telescope, our most precise space instrument, points with accuracy measured in milliseconds about 40 times less precise than what we'd need. But wait, it gets worse. Earth is rotating. Earth is orbiting the sun. The sun is moving through the galaxy, all at different speeds and angles. Your laser array needs to compensate for all of this motion in real time while maintaining that nanometer level precision. It's like trying to thread a needle while riding a roller coaster, and the needle is on another roller coaster going the opposite direction. Challenge number 2. The atmosphere. Earth's atmosphere is constantly moving, changing temperature, density fluctuating. This causes something called atmospheric turbulence, the same thing that makes stars twinkle. It distorts laser beams. Try shining a laser pointer through a candle flame and watch how the beam dances and bends. Now imagine trying to maintain a focused beam through 100 kilometers of atmosphere, with weather patterns, clouds, temperature gradients, all bending and scattering your light. This is why serious proposals involve building the laser array in space, either in Earth orbit or on the Moon. On the Moon, you'd have a stable platform with no atmosphere, no weather, and the Moon rotates much slower than Earth. But now you're talking about building a kilometer-wide laser array on the Moon. The logistics of that are staggering. Every component has to be launched from Earth. Every piece has to be assembled by robots or astronauts. We've never built anything that large and complex beyond Earth orbit. Challenge number 3. Power. Remember, we're talking about 50 to 100 gigawatts. That's the power consumption of a medium-sized country. Where does that energy come from? Solar panels? You'd need a solar farm the size of a small nation. Nuclear reactors? You'd need dozens of them, and somehow you have to launch all that mass into orbit or to the Moon. Each Starshot probe only gets fired at for about 10 minutes, but during those 10 minutes, you're consuming enough energy to power New York City for a week. Kevin Parkin, a physicist working on the project, proposed a potential solution. Build the laser array in stages. Start with a smaller array that can achieve maybe 5% light speed. As technology improves and gets cheaper, expand it. Use the same infrastructure to launch multiple missions over decades. Amortize the cost across hundreds of launches. But even this small version would be one of the largest construction projects in human history. Challenge number 4, the sail itself. This might actually be the most mind-bending engineering challenge of all. You need a material that is incredibly reflective, at least 99.99% reflective, because any absorbed light becomes heat. At the power levels we're talking about, even 0.001% absorption means the sail would vaporize instantly. It needs to be extraordinarily thin to minimize mass, but strong enough to not tear apart under the acceleration forces. And it needs to maintain its shape and reflectivity in the harsh environment of space. Harry Atwater, a materials scientist at Caltech working on Starshot, is developing metamaterials-engineered structures with properties not found in nature. They're working with sheets of material, just a few hundred atoms thick, patterned with nanoscale structures that reflect light with unprecedented efficiency. These materials barely exist in laboratories right now. We're talking about scaling them up to sails tens of meters across. Think of it like this. Imagine trying to make a mirror the size of a basketball court, thinner than a soap bubble, more reflective than the finest telescope mirror, strong enough to survive being hit by a laser that could vaporize steel, and light enough that the entire thing weighs less than a paperclip. That's what we need. Challenge number 5, the probes themselves. A computer the size of a microchip that can survive 20 years in space, withstand intense laser heating during launch, navigate through the radiation environment of interstellar space, take high-resolution photos while traveling at 134 million miles per hour, and then beam that data back across 4.37 light years using a laser powered by what, exactly? The probe is too small for solar panels to generate meaningful power. Nuclear batteries? Too heavy. There's research into using the probe's own motion through the cosmic microwave background radiation to generate tiny amounts of power, but that's still theoretical. Mason Peck, former chief technologist for NASA, points out another problem: communication. When the probe transmits data back to Earth, it's sending a laser signal from 25 trillion miles away. The beam will spread out. By the time it reaches Earth, we'll need receivers with kilometer-wide apertures just to detect the signal. And the data rate will be incredibly slow, maybe a few bits per second. It would take months or years to download a single high-resolution image. Challenge number 6, timing. The laser only fires for about 10 minutes while the probe is within range. But the probe is accelerating the entire time, constantly speeding up. The laser needs to track this acceleration perfectly, adjusting its aim continuously as the probe gets faster and farther away. If the laser loses track of the probe, even for a fraction of a second, the probe misses its target velocity and might take hundreds of years to reach Alpha Centauri instead of 20. There's also synchronization. If you're launching thousands of probes, they need to be spaced precisely so the laser can fire at each one without the array overheating or running out of power. It's like coordinating a machine gun that fires once every few minutes, but each bullet costs millions of dollars and takes 20 years to reach its target. And here's a problem nobody talks about. Once the probe is up to speed, how does it orient itself? How does it know where to point its cameras when it reaches Alpha Centauri? At 20% light speed, you have relativistic effects, time dilation, length contraction. The stars won't be where the probe expects them to be due to aberration of light. The probe needs to compensate for relativistic effects with a computer that has less processing power than your phone, running on nanowatts of power, 20 years from now, when it's received no software updates and no human can help if something goes wrong. You might be thinking, this is impossible. These challenges are insurmountable. And honestly, 10 years ago, you would have been right. But here's what's changed. Here's why brilliant minds like Stephen Hawking thought this could actually work. And this is going to completely reframe how you think about technological progress. In 1965, Gordon Moore, co-founder of Intel, noticed something remarkable. He observed that the number of transistors on a microchip was doubling approximately every 2 years. This became known as Moore's Law, and it's held true for nearly 60 years now. Your smartphone has more computing power than all of NASA had when they sent astronauts to the moon. That's not an exaggeration. It's literally true. But here's what most people don't realize. Moore's Law isn't just about computers. It's happening with lasers too. The cost per watt of laser power has been dropping exponentially. In 1985, a 1-watt laser cost about $1,000. Today, you can buy a 1-watt laser pointer for $20. That's a 50-fold improvement in price performance. Material science is advancing exponentially too. We can now engineer materials at the atomic level, creating structures impossible just a decade ago. Philip Lubin's insight was this: we don't need to solve all these problems perfectly right now. We need to solve them well enough that exponential technological improvement will handle the rest. And the timeline works out almost perfectly. Think about it. If we started building the laser array today, it would take 15 to 20 years to construct and test. But 20 years from now, laser technology will be about 1,000 times better than it is today if current trends continue. Material science will have advanced similarly. Computer chips will be phenomenally more powerful and efficient. By the time the infrastructure is ready, the technology will have caught up to our needs. This is called the technological runway approach. You start building the framework now, knowing that the components will improve as you build. It's like how NASA designed the space shuttle in the 1970s using slide rules and blueprints, but by the time it flew, they had computers to help manage it. Except this is that same principle on steroids, applied to literally every component of the system. Researchers at the University of California, Santa Barbara, where Lubin works, have already built prototype laser arrays. They're small, just a few meters across, but they've demonstrated proof of concept. They've pushed tiny reflective test objects using laser light. They've measured the efficiency, tested different wavelengths, tried various configurations. The physics works. It's not theory anymore. It's engineering. Gary Hughes, a physicist at California Polytechnic State University, has designed targeting systems using adaptive optics, the same technology that helps ground-based telescopes compensate for atmospheric turbulence. These systems can track fast-moving objects with incredible precision by analyzing the distortion of a reference laser beam and adjusting the main beam in real time. The technology exists right now in telescopes. It just needs to be scaled and adapted. The sail materials are advancing faster than anyone expected. In 2018, researchers created a reflective material that's 99.9996% reflective, that's absorbing only 4 parts per million. It's made of alternating layers of materials, just nanometers thick, creating interference patterns that bounce almost all light. And it's incredibly light. A sail the size of a bed sheet weighs less than a gram. These aren't theoretical anymore. You can hold them in your hands. What about power? Here's where the economics get interesting. The cost of solar power has dropped by 90% in the last decade. Some projections suggest that by 2040, solar energy will be essentially free. The panels will last longer than the time it takes to pay them off. A 100 gigawatt solar array sounds absurd today, but if energy becomes cheap enough, it's just a matter of land area. You'd need about 200 square kilometers of solar panels. That's a lot, but it's smaller than many cities. And if you build it in the desert where land is cheap and sunshine is abundant, the economics start to work. Or consider space-based solar. Japan and China are both working on orbital solar power stations that would beam energy to Earth. If that technology matures, you could beam power directly to your lunar laser array. The moon has no atmosphere to block sunlight, and a solar array that would work essentially 24/7 except during lunar night. There's another exponential curve working in our favor. Launch costs. In 2010, it cost about $10,000 to put a kilogram in orbit. Today, With SpaceX's reusable rockets, it's closer to $1,500 per kilogram. Starship, if successful, could drop that to under $100 per kilogram. If that trend continues, launching the components for a lunar laser array becomes economically feasible. Pete Worden, former director of NASA Ames Research Center and executive director of Breakthrough Starshot, has said that if current trends continue, the entire project could cost around $10 billion. That sounds like a lot until you realize that's the cost of a single aircraft carrier. The United States alone has 11 of them. Globally, we spend over $2 trillion per year on military budgets. From that perspective, $10 billion to become an interstellar species seems like the bargain of the millennium. But here's what really makes this feasible. You don't need to build everything at once. You can start small. Launch one probe as a technology demonstration. Build a small laser array, maybe in Earth orbit first. Test it on progressively faster and farther targets. Each mission teaches you what works and what doesn't. Each success builds momentum, attracts funding, improves the technology. This is exactly how space exploration has always worked. We didn't start by sending humans to the moon. We started with tiny satellites, then small probes, then animals, then humans in Earth orbit, then lunar orbit, then landing. Each step built on the previous one. Starshot can follow the same path. In fact, that's already happening. The breakthrough initiatives, funded by Yuri Milner, have already spent over $100 million on research and development. Universities around the world are working on different pieces of the puzzle. The European Space Agency is interested. China has expressed interest. This isn't one crazy scientist's fever dream anymore. This is a serious international effort with real funding, real research, and real progress. Now here's the question nobody's asking yet, but it's going to blow your mind when you think about it. What happens when we actually succeed? What happens when we send these probes to Alpha Centauri and they send back data? Because the implications are so profound, so civilization-altering, that they completely dwarf the technological achievement itself. Let's imagine it's 2050. The first wave of Starshot probes was launched in 2030. They've been traveling for 20 years at 20% light speed. They're about to reach Alpha Centauri. Back on Earth, arrays of receivers, massive radio dishes, and optical telescopes are pointing at that tiny point in the sky, waiting. Everyone knows this is happening. It's been building for 2 decades. Children have grown up knowing that someday soon, we'll see another star system up close for the first time. And then the signal arrives. First, just a carrier wave confirming the probes survived the journey. Then, slowly, bit by bit, the first image begins to download. It takes weeks. Every day, more pixels fill in. The world watches as an alien sun comes into focus. Not science fiction, not an artist's rendering. A real photograph of Alpha Centauri A, our closest stellar neighbor, taken from just a few billion miles away. What if I told you that moment, that one image could be more significant to human civilization than the invention of the printing press, the discovery of the Americas, or the moon landing? Here's why. Right now, in 2026, we know of over 5,000 exoplanets, planets orbiting other stars. We've detected them using indirect methods. We see the star dim slightly when a planet passes in front. We see the star wobble from the planet's gravity. But we've never seen one up close. We've never actually taken a picture with enough resolution to see what's there. We're like people in the 1400s who knew there were other continents but had never seen them. Alpha Centauri is actually a triple star system. There's Alpha Centauri A and B, 2 sun-like stars orbiting each other, and Proxima Centauri, a small red dwarf that orbits the pair. And here's what's absolutely wild. In 2016, astronomers discovered a planet orbiting Proxima Centauri. It's called Proxima Centauri b. It's about the same mass as Earth, and it orbits in the habitable zone, the distance from its star where liquid water could exist. Let me say that again. The closest star to our sun has a potentially habitable planet orbiting it. We have a neighbor, maybe. But here's what we don't know. Is there water? Is there an atmosphere? If there's an atmosphere, what's in it? Are there any biosignatures, chemical signs of life? We can't tell from Earth. The planet is too far away, too small, too close to its star. Our telescopes can barely confirm it exists, let alone see any details. The Starshot probes would change that. As they fly through the system in those few hours of closest approach, they'd photograph Proxima b, high-resolution images. Spectroscopy to analyze any atmosphere. Measurements of magnetic fields, radiation levels, temperature. We'd finally know, is there a world out there that could harbor life? Guillaume Anglade-Escud, the astronomer who discovered Proxima b, has said that even confirming the planet is truly Earth-like would be revolutionary. But what if the probes found more? What if they found chemical signatures inconsistent with geological processes alone? What if they found patterns in the atmosphere suggesting biological activity, oxygen and methane, in ratios that only make sense with life? We wouldn't be alone anymore. Not in the sense that we've made contact with aliens, but in the sense that we'd have proof that life exists beyond Earth. The philosophical implications are staggering. Every religion would need to grapple with it. Our place in the universe would fundamentally shift. We'd be one species among countless others. Or imagine the opposite. The probes arrive and find nothing. Proxima b is a dead rock. No atmosphere. No water. No life. Alpha Centauri A and B have no planets in habitable zones. Our nearest stellar neighbor is a wasteland. That's almost as profound. It would suggest life might be incredibly rare. Earth might be precious in a way we never fully appreciated. The great filter, the hypothesis that something prevents civilizations from becoming spacefaring, might be real, and we haven't encountered it yet. Either answer changes everything. This is why Stephen Hawking was so passionate about this project before he died. He understood that the technological achievement of getting there is important, but what we might learn is transcendent. But there's another layer to this that's even more mind-bending. Here's what will really blow your mind. We wouldn't just be exploring one star system. Once we've built the infrastructure to reach Alpha Centauri, we could point it at any star within a dozen light years. Barnard's star 5.96 light years away. Sirius 8.6 light years. Tau Ceti 11.9 light years. Dozens of stars become accessible. And many of these stars have planets. Tau Ceti has at least 4 planets, possibly 5. Some are in or near the habitable zone. Imagine sending probe swarms to multiple star systems simultaneously. Within a single human lifetime, we could have reconnaissance data from a dozen different solar systems. We'd see planetary formation at different stages. We'd see different types of stars and their effects on planetary environments. We'd essentially fast-forward our understanding of planetary science by centuries. Sarah Segar, an astrophysicist at MIT famous for her work on exoplanets, has described this as the great reconnaissance of the 21st century. We'd go from knowing almost nothing about other star systems to having actual survey data from dozens of them. The scientific return would be incomprehensible in its scope. But here's where it gets personal. Here's where this stops being about abstract science and starts being about you, sitting there right now, watching this video. Because this project represents something deeper than exploration. It represents a choice humanity is making right now about what kind of species we want to be. Think about it. We live in an era of unprecedented challenges. Climate change, political polarization, economic inequality, wars, pandemics. It would be easy to turn inward, to focus only on Earth's problems, to say we can't afford to dream about the stars. And there are legitimate voices saying exactly that. Why spend billions on space when people are suffering on Earth? But here's the counter-argument, and this is crucial. Humanity has never been good at doing just one thing. We don't choose between solving problems at home and exploring. We do both. The same technologies developed for Starshot have terrestrial applications. Laser technology advances communication, manufacturing, medicine. Materials science breakthroughs help build better solar panels, stronger structures, more efficient electronics. The targeting systems improve everything from self-driving cars to medical imaging. But more than that, and this is what really matters, projects like this give us something to unite around. They remind us that we're one species with one origin on one small planet. They make our tribal conflicts seem petty. They give us a shared purpose that transcends nationality, religion, politics. When the Apollo astronauts took the famous Earthrise photo in 1968, Earth rising above the lunar horizon, it sparked the environmental movement. Seeing our planet from outside made people realize how fragile and precious it is. That one image changed human consciousness. Imagine what happens when we send back images of other worlds, other suns, when we have to contend with the reality that we're citizens of a cosmos, not just a country. Avi Loeb has argued that becoming interstellar is an existential imperative. The sun won't shine forever. In about 1 billion years, Earth will become uninhabitable as the sun heats up. In 5 billion years, the sun will expand into a red giant and literally consume Earth. If humanity is to survive long term, we're talking timescales of millions or billions of years. We need to become a multi-planetary, eventually multi-stellar species. Starshot is the first real step toward that future. But you don't have to think on billion-year timescales to see the value. You just need to think about what it means to be alive at this moment in history. Every human who ever lived before us lived in a universe where interstellar travel was pure fantasy. Every human who lives after us will live in a universe where we know what's around the nearest stars. We're alive during the transition. We're the generation that makes this leap. That's not just cool. That's cosmically significant. And here's what gets me emotional. This isn't being done by governments alone. This is funded in part by private citizens who just want to see it happen. Yuri Milner made his fortune in technology and decided to spend $100 million to help humanity reach the stars. Not for profit, not for power. Because it's important. Because it matters. Stephen Hawking spent his final years advocating for this project because he believed in it. And you watching this right now, you're part of this too. By learning about it, by sharing this knowledge, by supporting the idea that humanity should explore beyond Earth, you're contributing to a cultural momentum that makes these projects possible. Governments fund what citizens care about. Engineers work on what excites them. Every person who looks up at the stars and wonders what's out there and could we go there is part of the reason this is happening. So let me ask you something, and I really want you to think about this. What would it mean to you personally if, in your lifetime, you saw photographs of planets around another star? Not in a textbook as an artist's concept, but real images taken by spacecraft we built? How would that change your perspective on your own life, your problems, your place in the universe? I want you to comment below with your honest answer, because I think this is the most important conversation humanity is having right now, and most people don't even know it's happening. And make sure you're subscribed, because we're about to go even deeper. We're going to talk about the philosophical implications that nobody is discussing yet, the stuff that will keep you up at night. Let's talk about something that most coverage of Starshot completely ignores. We're so focused on the technology, the engineering, the can we do it, that we're not asking a much deeper question, should we? And not in a simplistic, is it worth the money way, but in a profound philosophical sense about what it means to explore, to intrude, to potentially contaminate, or discover things we're not prepared for. Here's a thought experiment. Imagine the Starshot probes reach Proxima Centauri b and confirm it has life. Not intelligent life, but microbial life. Bacteria-like organisms in the soil or oceans. Actual alien biology. The first proof that Earth isn't unique? Now imagine this. One of the probes crashes on the surface. It's traveling at 20% light speed. Remember, even a tiny chip-sized probe would hit with the force of a small bomb. And on that chip are Earth microbes. We can sterilize spacecraft, but we can never guarantee 100% sterilization. DNA is incredibly resilient. Tardigrades, microscopic animals from Earth, can survive the vacuum of space, extreme radiation, temperatures near absolute zero. What if we accidentally seed another world with Earth life? What if our microbes kill their microbes through competition? What if we destroy the only other example of life in our cosmic neighborhood before we even understand it? This is called forward contamination, and it's a real ethical dilemma that planetary protection officers at NASA worry about. Or flip it around. What if there's life on Proxima b, and when the probes fly through, they pick up alien microbes in their instruments and beam back not just data, but genetic information? Not the microbes themselves. They can't survive the journey back, but the information about their DNA or equivalent. What if we then synthesize that biology in a lab on Earth to study it? Have we just committed the greatest act of biopsy in history? Have we stolen the genetic heritage of another world? These aren't just abstract ethical questions. They have legal implications. The Outer Space Treaty of 1967 requires nations to avoid harmful contamination of space and celestial bodies. But the treaty was written when nobody thought we'd be reaching other star systems. Does it apply to Alpha Centauri? Who has jurisdiction over what happens there? What if China sends probes with different contamination standards than the United States? What if a private company wants to mine asteroids in another star system someday? Who has the authority to allow or prevent that? Here's another angle that'll twist your brain: ownership and discovery. When Columbus reached the Americas, he claimed them for Spain. Never mind that people already lived there. From a European perspective, it was discovery and therefore ownership. We recognize now how problematic that worldview was. But what about worlds with no intelligent life? If a Starshot probe is the first human artifact to reach Proxima b, does that give us any claim to it? The Antarctic Treaty System provides a possible model. Antarctica is the only continent with no native human population, and the treaty declares it a scientific preserve belonging to all humanity. No country can claim it. Military activity is prohibited. But that treaty works because Antarctica is on Earth, accessible, and nations can monitor compliance. How do you enforce similar agreements across light years? Let's get even weirder. What if we find signs of extinct intelligent life? Ancient ruins on a planet that once had a civilization, now dead for millions of years. Do those belong to us to study? Are we archaeologists or grave robbers? What if we find data storage devices, an alien hard drive with their accumulated knowledge? Do we have the right to access it? Or is that violating the privacy of an extinct species? Some philosophers argue we have a moral obligation to preserve information. If a civilization's knowledge would otherwise be lost forever, doesn't the universe benefit from us preserving it? Others argue that civilizations have a right to be forgotten, to not have their ruins picked through by aliens. John Traffigan, a professor of religious studies at the University of Texas, who studies the ethics of space exploration, points out an even stranger possibility. What if we find life, but it's so fundamentally different from Earth life that we don't recognize it? What if it's not carbon-based? What if it doesn't use DNA? What if it exists in a form we can't even conceptualize as life because it doesn't meet our biological definitions? We could destroy it without even knowing it exists. We could be looking right at it with our instruments and not see it because we're looking for the wrong signatures. This is called the shadow biosphere problem, and it keeps astrobiologists up at night. But here's a question that really messes with me. What if we're not the first? What if another civilization, millions of years ago, did something similar? What if there are already probes from other species exploring the galaxy, and they passed through our solar system long before humans existed? What if they're watching us right now, waiting to see if we're intelligent enough to join the club of spacefaring species? This sounds like science fiction, but it's a serious hypothesis called the zoo hypothesis. The idea that intelligent aliens exist, but deliberately don't contact us, either to let us develop naturally or because we're not interesting enough yet. James Benford, a physicist who works on interstellar communication, has suggested we should be looking for alien probes at gravitationally stable points in our solar system, places where objects naturally collect. Maybe there's an ancient probe sitting at one of Earth's Lagrange points, dormant for eons, waiting for signs of intelligent life. If that's true, then Starshot isn't just exploration. It's us announcing ourselves to the cosmos. It's us saying, we're here, we're capable, we're ready to explore. And that could trigger, what? First contact? An invitation to something bigger? Or nothing, because we're alone. Frank Drake, the astronomer who created the famous Drake equation to estimate the number of intelligent civilizations in the galaxy, believed that once a species becomes capable of interstellar communication or travel, they inevitably do it, because the alternative is staying silent and isolated. And what kind of species chooses that when the option exists to reach out? But Enrico Fermi asked the question that haunts everyone in this field: where is everybody? If life is common, if intelligence arises naturally, if space travel is possible, where are all the aliens? Why haven't we seen evidence of them? The Fermi paradox suggests maybe we're the first. Or maybe we're the last. Maybe civilizations destroy themselves before becoming interstellar. Or maybe space is so vast and civilization so rare that we're unlikely to ever meet. Starshot could help answer this. If we explore a dozen star systems and find no life anywhere, that's data. That suggests life is rare, intelligence rarer still, and we should be very, very careful with our own civilization, because we might be the only ones. But if we find life everywhere, that suggests the universe is teeming with biology, and the great silence is even more mysterious. Why hasn't anyone built a Dyson sphere? Why haven't we detected megastructures or stellar engineering? Some thinkers, like Robin Hanson, who coined the term Great Filter, suggest there's something that prevents civilizations from spreading across the galaxy. Either it's behind us, maybe the jump from non-life to life is incredibly rare, and we're lucky to exist, or it's ahead of us, and something wipes out civilizations before they can expand. That's a terrifying thought. What if interstellar travel itself is the filter? What if there's a reason nobody's doing it? But here's a more optimistic interpretation. Maybe we're early. The universe is 13.8 billion years old, but stars like our sun metal-rich stars, capable of forming rocky planets, only became common in the last few billion years. Maybe intelligent life is a recent phenomenon cosmically, and we're among the first species capable of reaching the stars. Maybe in 1,000,000 years, the galaxy will be full of civilizations, and we'll be remembered as one of the pioneers. That possibility that we could be the first, the ones who prove it's possible, the ones who start the chain reaction of life, spreading across the cosmos, that's humbling and terrifying and exciting all at once. It means everything we do matters. Every decision we make about how to explore space ethically, how to treat potential life, how to leave our mark, it sets precedents for everyone who comes after. And look, I know this is heavy. I know we've gone from cool laser spacecraft to existential questions about humanity's cosmic role, but this is important, because the technology is moving faster than our philosophy. We could launch Starshot within 20 years, but have we agreed on what we'll do if we find life? Have we established protocols? Have we thought through the implications? The Committee on Space Research, COSPER, has planetary protection policies, but they're focused on our solar system. There's no international agreement on how to handle discoveries around other stars. We need to be having these conversations now, not scrambling to figure it out when the probes are already launched. So here's what I want you to think about, and this is crucial. If you were on the ethics committee deciding the rules for Starshot, what would you say? Should we avoid planets that might have life? Should we deliberately target them to learn more? Should we build in self-destruct mechanisms so probes don't contaminate if they crash? Should we even go at all? Or wait until we're more mature as a species? I genuinely want to know what you think. Drop a comment with your take. Because unlike most of history, where a handful of people made decisions that affected everyone, this is a decision all of humanity needs to make together. And the conversation starts here, with people like you who care enough to watch a 3-hour video about interstellar exploration. Now, let's talk about something that might actually blow your mind more than anything else we've covered. What happens to time itself at the speeds we're talking about? Because we haven't discussed relativity yet, and once you understand what these probes experience, you'll never think about space travel the same way again. Okay, here's where things get seriously weird. We've talked about Starshot probes traveling at 20%, the speed of light, 134 million miles per hour. That sounds fast, but it's actually slow enough that relativistic effects are minimal. But let's talk about what happens if we scale this up. What if future versions of this technology could reach 50% light speed? 90%? 99.9%? Because the physics at those speeds is so counterintuitive, so mind-bending, that it fundamentally changes what interstellar travel even means. Albert Einstein's special relativity, published in 1905, revealed something extraordinary. Time is not absolute. Time passes differently depending on how fast you're moving. This isn't theory, it's been proven over and over. GPS satellites have to account for time dilation, or they give you wrong directions. Particle accelerators see it every day, with subatomic particles living longer than they should, because they're moving so fast time slows down for them. Here's the equation, and I promise this is worth understanding. Time dilation is calculated by dividing 1 by the square root of 1 minus v squared over c, where v is your velocity and c is the speed of light. Let me show you what this means practically. At 20% light speed, our current Starshot target time dilation is minimal. For every 10 years that pass on Earth, the probe experiences about 9.8 years. Barely noticeable. But watch what happens as we go faster. At 50% light speed, for every 10 years on Earth, the probe experiences about 8.7 years. Getting more noticeable. At 90% light speed, for every 10 years on Earth, the probe experiences only 4.4 years. Time is moving less than half as fast for the probe. At 99% light speed, for every 10 years on Earth, the probe experiences only 1.4 years. Time has slowed to a crawl. At 99.9% light speed, for every 10 years on Earth, the probe experiences only 5 months. Time is passing 22 times slower. At 99.99% light speed, and this is where it gets absolutely insane, for every 10 years on Earth, the probe experiences only 17 days. Time is passing 214 times slower. Do you see what this means? If we could build a probe that travels at 99.99% light speed, it could cross the galaxy 100,000 light-years in what feels like only 470 years from the probe's perspective. You'd still need 100,000 years of Earth time, but the probe wouldn't experience it that way. If you put a human on that probe, which is physically impossible for many reasons, but go with me, they could cross the galaxy in less time than has passed since Columbus landed in America. Kip Thorne, the Nobel Prize-winning physicist who worked on the movie Interstellar, has calculated even more extreme scenarios. At 99.999% light speed, you could theoretically travel to the Andromeda Galaxy, 2.5 million light-years away, in about 32 years of ship time. The universe would age 2.5 million years. Earth would be long gone. Everything you knew would be dead for millennia. But from your perspective, It's a career-length journey. This is simultaneously the most hopeful and most depressing thing about interstellar travel. The speed of light isn't a prison for the traveler. It's a prison for everyone they leave behind. You could explore the stars, but you could never come home. Everyone you knew would be dead. Your entire civilization might be gone. You'd be a time traveler into the future, one way with no possibility of return. This is called the twin paradox. If one twin stays on Earth and the other travels at near light speed, when they reunite, the traveling twin is younger, significantly younger. It's been proven with atomic clocks on airplanes. At relativistic speeds, the effect is dramatic enough that the traveling twin could be decades or centuries younger than the stay-at-home twin. But there's another relativistic effect that's even weirder: length contraction. As you approach light speed, space itself contracts in your direction of travel. At 99.99% light speed, distances shrink to 1/214th of their rest length. A journey that's 100 light years from Earth's perspective would feel like only 0.47 light years to you. Space itself compresses. This means, from the probe's perspective, it's not traveling 4.37 light years to Alpha Centauri. It's traveling a fraction of that. The universe literally becomes smaller the faster you go. It's like a cosmic cheat code. But here's the catch, and this is where the engineering becomes nightmarish. The faster you go, the more dangerous space becomes. Remember how we talked about dust? At 20% light speed, a grain of sand is dangerous. At 99% light speed, a single hydrogen atom has kinetic energy equivalent to a bullet. The sparse hydrogen that exists in interstellar space, about 1 atom per cubic centimeter, becomes deadly radiation. You'd need shielding so thick it defeats the purpose of going fast. This is called the interstellar medium problem. And it's one of the main reasons we can't just crank up the speed indefinitely. Robert Zubrin, an aerospace engineer, calculated that a spacecraft traveling at 95% light speed would need a shield weighing millions of tons to protect against interstellar hydrogen. And that's just hydrogen hitting anything solid would be catastrophic. There's also the Doppler effect. Light coming from in front of you gets blue shifted toward higher energy. The cosmic microwave background radiation harmless radio waves that fill the universe, it's blue shifted into deadly gamma rays. At high enough speeds, the universe ahead of you becomes a blinding wall of radiation. At 99.99% light speed, the CMB radiation would kill you. James Benford has suggested a possible solution. Use your magnetic field as a shield. Generate an enormously powerful magnetic field around your spacecraft that deflects charged particles. This is how Earth's magnetosphere protects us from solar wind. But at relativistic speeds, you'd need a field thousands of times stronger than anything we can currently create, and it would require massive amounts of power to maintain. Or there's the Bussard ramjet concept, proposed by physicist Robert Bussard in 1960. Instead of carrying fuel, use a giant magnetic scoop to gather hydrogen from interstellar space and use it as fusion fuel. The faster you go, the more hydrogen you collect, so you're simultaneously shielding yourself and fueling your engine. It's an elegant idea, but the engineering is far beyond our current capabilities. You'd need a magnetic scoop thousands of miles wide. Here's another mind-bending aspect of relativity: the relativity of simultaneity. Events that are simultaneous from one perspective aren't simultaneous from another. If you're traveling at near light speed toward Alpha Centauri, when you see events happening on Earth through a telescope, you're seeing them from a different time frame than Earth observers would agree on. Let's say you launch at 99% light speed. From Earth's perspective, you arrive at Alpha Centauri in about 4.4 years. From your perspective, only 0.6 years passed. But here's the weird part. Because of your velocity, your now, what counts as the present moment for you, is different from Earth's now. When you arrive at Alpha Centauri, from your frame of reference, Only about 4 years have passed on Earth. Not the 4.4 years Earth observers measure. Time is literally relative to your motion. This gets even stranger with the Andromeda paradox. Right now, whether a specific event has already happened in the Andromeda galaxy depends on your motion. If you're walking toward Andromeda, the event might have already happened in your reference frame. If you're walking away, it might not have happened yet. The very concept of now breaks down across cosmic distances. Physicist Brian Greene describes this as the universe being like a giant block of spacetime, where all of time past, present, future exists simultaneously. And what we call now is just our slice through it, dependent on our motion. This is called the block universe interpretation, and it has profound implications for free will, determinism, and the nature of time itself. But let's bring this back to Starshot. Even at 20% light speed, we're tapping into these effects. The probes experience slightly less time than Earth. The distances are slightly contracted from their perspective. And here's what's beautiful. We can measure this. When the probes send back their data, we can compare their onboard clocks with Earth clocks and directly observe time dilation. We can test Einstein's predictions with probes traveling across light years. That's not just engineering. That's fundamental physics research. And this is why some scientists are pushing for faster speeds, even if it's harder. Yes, 20% light speed gets us to Alpha Centauri in 20 years. But 50% light speed gets us there in 8 years. 90% light speed in less than 5 years. Each increment matters because we're racing against human lifespans. The difference between getting data back in 25 years versus 10 years is the difference between the people who launched the mission being retired versus still working. It's the difference between the scientists who designed the probes seeing the results or not. There's a poignant calculation called the weight equation, developed by Andrew Kennedy, a British researcher. It asks, should you launch an interstellar mission now with slower technology, or wait for technology to improve and launch later with faster technology? If technology improves fast enough, waiting might get you there sooner, even though you launch later. But if you wait too long, you might never launch at all, because you're always waiting for the next improvement. Kennedy calculated that for missions to nearby stars, with current rates of technological improvement, the optimal time to launch is, well, it depends on how fast you think technology is improving. Some models say we should launch now. Others say wait 20 years. But everyone agrees you can't wait indefinitely, because eventually improvements slow down and you've just wasted time. This creates a fascinating strategic dilemma. Do we launch Starshot at 20% light speed now? Or do we wait a few decades for better lasers, better sails, and aim for 30% or 40% light speed? There's no objectively right answer. It depends on what you value more, getting data sooner or getting more comprehensive data with more advanced technology. Stephen Hawking advocated for launching sooner rather than later. His argument was simple. We don't know how much time we have. Climate change, nuclear war, asteroid impacts, pandemics, there are existential risks to humanity. The sooner we become interstellar, even if just with probes, the safer our knowledge and legacy becomes. If something wipes out humanity, but our probes are out there, carrying information about who we were, we haven't entirely disappeared. Carl Sagan made a similar argument with the Voyager Golden Record phonograph records placed on the Voyager spacecraft, containing sounds and images from Earth. They're now in interstellar space, carrying a message from humanity to whoever or whatever might find them billions of years from now. Sagan called them a gift from a small, distant world and a message of hope. Starshot probes could carry similar messages, but they'd actually reach other star systems, not just drift through empty space. Imagine that a message from humanity delivered to another solar system, carrying our music, our art, our science, our history. Not as a transmission that fades over distance, but as a physical object that arrives and could last for billions of years. That's not just exploration. That's making a mark on the cosmos. It says we were here. We wondered. We reached out. And that brings me to something I've been building up to this whole time. Something that ties all of this together. The technology, the physics, the philosophy, the human drive to explore. We need to talk about why this matters to you personally. Not humanity in abstract, not future generations. You, right now, in your life. Because this is about to get deeply personal. I want you to stop and think about something for a moment. How many times have you looked up at the night sky and felt small? How many times have you felt like your problems, your life, your existence doesn't really matter in the grand scheme of things? Be honest, we all feel that way sometimes. The universe is 13.8 billion years old and contains 2 trillion galaxies. We live for maybe 80 years on a rock that's existed for 4.5 billion years. We're fleeting specks of consciousness in an incomprehensibly vast cosmos. But here's what I want you to understand, and this is the most important thing I'm going to tell you. That feeling of insignificance is based on a fundamentally wrong way of thinking about significance. You know what's actually rare in the universe? Not stars. There are billions of trillions of them. Not planets. We found thousands, and there are probably billions just in our galaxy. Not even atoms. There are more atoms in a glass of water than there are glasses of water in all of Earth's oceans. You know what is rare? Consciousness, awareness, the ability to look at the universe and understand it, the ability to ask questions, to wonder, to create, to care about truth. As far as we know, consciousness might be the rarest thing in the entire cosmos. We haven't found it anywhere else. It might exist only here, only in you and me and the other 8 billion people on this planet. And if consciousness is rare, then you, your specific consciousness, with your specific experiences and thoughts and feelings, might be literally unique in all of existence. Think about that. There might be trillions of planets, but there's only one you. There has never been someone exactly like you in all of history. There will never be someone exactly like you again. Your consciousness, your perspective, your subjective experience of existence, that's not insignificant. That's cosmically precious. And here's where Starshot connects to this. You are alive at the only moment in all of human history when we're transitioning from a planetary species to an interstellar one. Every human who ever lived before you, billions of people across thousands of generations died without knowing what's around the nearest stars. They could only wonder. They could only imagine. But you might actually know. In your lifetime, you might see real photographs of planets around Alpha Centauri. Do you understand how special that is? You're not some random person born in a random time. You're alive during one of the most significant transitions in the history of life on Earth. You're witnessing the moment when one of Earth's species, us, reaches beyond our solar system for the first time. That's not going to happen again. This is it. This is the moment. And you're here for it. When you were a kid, did you ever dream about space? About exploring other worlds? Most people do. It's almost hardwired into us, this curiosity about what's beyond the horizon. But somewhere along the way, most people lose that. They get caught up in daily life, in bills and jobs and responsibilities. The stars become something they don't think about anymore. But that curiosity never really dies. It just gets buried. And videos like this, projects like Starshot, they reawaken it. They remind you that there's more to existence than your immediate concerns. They give you permission to care about something bigger, something that will outlast you. And here's what I've realized. Caring about things bigger than yourself isn't escapism. It's not avoiding real life. It's actually the most real thing you can do. Because when you die, and you will die, we all will. What matters? The bills you paid? The career you had? Those things matter for your comfort and security while you're alive. but they don't give life meaning. What gives life meaning is being part of something that transcends your individual existence. Starshot is part of that. When those probes reach Alpha Centauri, the people who launched them might be dead, but the knowledge they send back will belong to all humanity. It will be used by scientists not yet born. It will inspire children who are currently in elementary school. It becomes part of the permanent legacy of our species. And you get to be part of that story. Not in some grandiose way. You don't have to be an engineer or a scientist. Just by caring, by understanding, by passing on the knowledge, you're a link in the chain. You're part of the cultural fabric that makes this possible. Viktor Frankl, the psychiatrist who survived the Holocaust, wrote that what humans need most isn't pleasure or power, but meaning. And meaning comes from being part of something larger than ourselves. He found meaning in the midst of unimaginable suffering by holding on to the idea that his experiences could teach others something valuable, that his suffering wasn't meaningless if it could help someone else. You don't need to suffer to find meaning, but you do need to connect to something beyond yourself. For some people, that's religion. For others, it's art or family or social causes. For me, and maybe for you, it's the exploration of the cosmos, the expansion of human knowledge, the pursuit of understanding our place in the universe. Here's something that gives me chills. 10,000 years from now, if humanity still exists, what will they remember about our era? They won't remember most of our politics. They won't remember our celebrities. They won't care about the things that dominate our news cycles. But they will remember that this was the era when we started reaching the stars. They'll remember Voyager leaving the solar system. They'll remember the first images from Alpha Centauri. They'll remember that we, this generation, took the first steps toward becoming an interstellar species. You're not just a passive observer of history. You're an active participant in one of the most important chapters ever written. And that should change how you think about your own significance. When you're having a bad day, when you're stressed about work or relationships or money, take a moment and look up. Those stars are still there. Those questions about what's out there are still waiting to be answered. And you're alive during the time when we're starting to answer them. That doesn't make your problems go away, but it puts them in perspective. It reminds you that you're part of something vastly larger. And here's something else. The fact that you're still watching this video, or over 2 hours, in tells me something about you. It tells me you're someone who cares about understanding. Someone who's willing to invest time and mental energy into learning about complex topics. Someone who values knowledge for its own sake, not just for practical application. That's rare. Most people won't watch a 3-hour video about interstellar travel. They're not worse people for that. They just have different interests, different priorities. But you're here. That makes you part of a self-selected group of people who think deeply about humanity's future, about science, about the big questions. And I want you to know that matters. The world needs people who think about more than just their immediate circumstances. Society advances because of people who care about understanding how things work, who get excited about discoveries, who support the idea that knowledge and exploration are worthwhile pursuits. Every scientist who works on Starshot, every engineer, every person who donated money to breakthrough initiatives, they all started as someone like you. Someone who looked up at the stars and wondered. Someone who watched a documentary or read a book and felt that spark of curiosity. Someone who decided that understanding the universe was something worth caring about. Maybe you'll never work directly on interstellar travel. That's okay. But by being informed, by caring, by sharing this knowledge with others, you're contributing. You're part of the ecosystem that makes these projects possible. You're part of the reason humanity is doing this. And when those first images come back from Alpha Centauri, when we see another solar system up close, for the first time, you'll be able to say you were there. You understood what was happening. You were part of the generation that made it possible. Your consciousness, your awareness, your caring It was part of the story. That's not insignificant. That's profound. So let me ask you, does Starshot matter to you? Do you care whether we reach Alpha Centauri in our lifetimes? Do you think humanity should explore the stars, even if it's hard, even if it's expensive, even if we don't know what we'll find? I want you to really think about that, because your answer tells you something important about yourself. It tells you what you value. It tells you what kind of future you want to help create. And if the answer is yes, if you do care, if you do think this matters, then don't keep it to yourself. Share this video. Talk about it with people. Help spread the idea that this is important, that this is possible, that this is happening right now in our lifetimes. Because the more people who care, the more likely it is to succeed. We're building momentum for something that will outlast all of us. And that's beautiful. Now, for the last section of this journey together, I want to talk about something that brings all of this together, the question of why. Why explore? Why reach for the stars? Why spend the resources, take the risks, push the boundaries? Because the answer to that question will change everything about how you see not just Starshot, but your own life. There's a famous quote, often attributed to Marcel Proust. The real voyage of discovery consists not in seeking new landscapes, but in having new eyes. I think that's partially true, but incomplete. The real voyage of discovery is both. You need to seek new landscapes and develop new eyes. And here's the thing about interstellar exploration. It forces both simultaneously. Let me tell you about something called the overview effect. It's a psychological phenomenon reported by astronauts who've seen Earth from space. Edgar Mitchell, Apollo 14 astronaut, described it as a sense of universal connectedness, seeing Earth as a tiny, fragile sphere floating in the void, no borders visible. No divisions apparent fundamentally changed how these astronauts saw themselves and humanity. Ron Garen, who spent time on the International Space Station, sighed, "When we look down at the Earth from space, we see this amazing, indescribably beautiful planet. It looks like a living, breathing organism. But it also, at the same time, looks extremely fragile." Many astronauts report coming back with a deep environmental consciousness and a sense that national conflicts are absurd when you've seen Earth as one unified whole. Now imagine the overview effect for our entire solar system. Imagine seeing our sun as just one star among billions, not from intellectual understanding, but from actual photographs taken from another star system. Imagine seeing our entire cosmic neighborhood as a tiny region of space that's all connected, all part of one larger structure. I think that will change human consciousness again. Just as seeing Earth from space sparked environmentalism, seeing our solar system from outside might spark a cosmic consciousness and understanding that we're all citizens of one star system, one interconnected region of spacetime. But there's a deeper reason for exploration that goes beyond any practical benefit or psychological effect. And this is where I'm going to get philosophical in a way that might seem abstract, but I promise it matters. The physicist Lee Smolin has argued that the universe has something like intentionality, not consciousness exactly, but a tendency toward complexity, toward creating structures that can process information. Stars create heavy elements. Planets create complex chemistry. Life creates reproduction and evolution. Brains create consciousness. Consciousness creates culture. Culture creates technology. Technology creates what? What's the next step? Some philosophers argue it's artificial intelligence. Others say it's the merger of biology and technology. But I think there's another possibility. It's consciousness spreading through the cosmos. It's the universe becoming aware of itself, not just in isolated pockets, but throughout its entire structure. Think about it. For 13.8 billion years, the universe existed without being observed. Stars formed and died. Galaxies collided. Black holes devoured matter. But there was no awareness of it, no consciousness to appreciate the beauty, to understand the mathematics, to ask why. Then, on at least one small planet around one ordinary star, the universe became self-aware. Atoms arranged themselves into patterns complex enough to contemplate their own existence. The universe could look at itself and ask, "What am I? How do I work? Where did I come from?" That's what consciousness is, the universe understanding itself. You are the universe becoming aware of itself. When you look at a sunset, that's the universe appreciating its own beauty. When you learn physics, that's the universe discovering its own rules. An exploration reaching beyond our planet, beyond our solar system, is the universe expanding its own awareness. It's not just humans being curious. It's consciousness itself, expanding outward, illuminating more of existence, bringing more of the cosmos into awareness. From this perspective, Starshot isn't just a science project. It's a step in a cosmic process. It's consciousness reaching outward, expanding the sphere of the universe that knows itself. Every new planet we photograph, every new star system we explore, we're expanding the region of the universe that has been observed, understood, known. And you might think, but it's just tiny probes sending back data. How is that cosmic consciousness? Here's how. That data comes back to Earth, where billions of minds can contemplate it. Each person who sees an image from Alpha Centauri becomes part of a collective awareness of that place. The knowledge spreads, becomes part of human culture, gets taught to children, influences art and philosophy and science. That solar system becomes part of our collective consciousness. It goes from being an abstract concept, Alpha Centauri exists, to being a real place that we know about, that we've seen, that we have a relationship with. The cosmos becomes more known, more real, more integrated into conscious experience. The philosopher Teilhard de Chardin called this the noosphere, the sphere of human thought. He believed that just as the biosphere is the realm of life on Earth, the noosphere is the realm of mind. And he thought it was growing, becoming more complex, more interconnected. That was back in the 1920s, before the internet. Imagine what he'd think now, with billions of minds connected digitally, sharing knowledge instantaneously. Starshot expands the noosphere beyond Earth. It makes the noosphere interstellar. Our collective knowledge, our shared awareness, stops being limited to one planet and starts encompassing multiple star systems. And here's what's profound. This might be rare in the universe. We don't know if other intelligences exist, but if they do, they probably went through this same transition. They probably had a moment where they realized they could leave their home star, where they chose to explore, where they decided to expand consciousness outward rather than staying isolated. This might be a test, not designed by anyone, but a natural filter. Civilizations either reach the stars or they don't. Either they overcome their divisions and their short-term thinking to pursue something larger, or they get stuck fighting over their home planet until something destroys them. We don't know which way humanity will go, but projects like Starshot push us in the right direction. They remind us we can think beyond our current problems. They show us we're capable of pursuing long-term goals that won't pay off in our lifetimes. They prove we can cooperate across nations and cultures for a shared purpose. In that sense, Starshot isn't just about reaching Alpha Centauri. It's about who we decide to be as a species. Are we short-sighted, tribalistic, self-destructive? Or are we capable of thinking cosmically, acting collectively, building for futures we'll never see? The answer isn't determined yet. We're writing it right now. Every decision we make about what to fund, what to value, what to work toward, these decisions are determining what humanity becomes. And you're part of that. I know I keep saying this, but it's crucial. You're not just a passive observer. Your values matter. What you care about ripples outward. The people you talk to, the ideas you share, the things you support, they all contribute to the collective direction of our species. If you think reaching the stars is important, act like it. Don't just passively agree. Actively support it. Follow the research. Share the news. If you can afford it, donate to organizations working on this. If you can't, just talk about it. Make it part of the conversation. Normalize the idea that becoming interstellar is a priority. Because here's the truth. These projects happen because enough people care. The moon landing happened because an entire nation decided it mattered. The James Webb Space Telescope exists because scientists convinced enough people that seeing the early universe was worth the cost. Starshot will happen if enough people believe it should. And the same is true for everything else that matters. Climate change will be addressed if enough people demand it. Poverty can be reduced if enough people care. Political systems can improve if enough people engage. The future isn't predetermined. It's created by the choices of millions of individuals, including you. So when you watch this video and feel that spark of excitement, that sense of wonder, that feeling that reaching the stars matters, don't let it fade. Hold on to it. Let it inform your choices. Let it remind you that you're part of something larger. Because at the end of your life, what will you be proud of? The times you played it safe? The times you focused only on yourself? Or the times you cared about something bigger, even when it was hard, even when the benefits weren't immediate, even when you couldn't see the direct impact? I think deep down, we all know the answer. We all want to be part of something meaningful. We all want our lives to matter, and they do matter. Every life matters because every conscious being is the universe becoming aware of itself. You are cosmically significant simply by existing, by being aware, by caring about truth. But you can amplify that significance. You can be not just a passive point of consciousness, but an active participant in the expansion of awareness. You can help push humanity toward the stars, toward knowledge, toward a future where we're not confined to one small world, but are spread across the cosmos, understanding more, experiencing more, becoming more. That's not fantasy. That's not wishful thinking. That's what's actually happening right now in your lifetime. Starshot is real. The technology is real. The funding is real. The scientists are real. This is happening. And when those first images come back from Alpha Centauri, when we see an alien sun up close, when we find out if Proxima b has oceans or is just a barren rock, when we discover whether we're alone or if life is everywhere, that moment will be one of the most significant in human history. You'll remember where you were when you first saw those images. You'll remember how it felt. And you'll be able to say, I was part of the generation that made this happen. I understood why it mattered. I cared when it counted. That's legacy. That's significance. That's what it means to live a life that matters. So as we close out this journey together, I want to leave you with one final thought. One question you should ask yourself. What will you do with this knowledge? Will you let it fade into the background, just another interesting thing you once watched? Or will you let it change you? Will you let it remind you that you're part of something vast and ancient and ongoing? Will you let it inspire you to think bigger, to care more, to contribute in whatever way you can to humanity's future? The answer is up to you. But whatever you decide, know this. The universe is watching through your eyes. The cosmos is experiencing itself through your consciousness. You are not separate from the stars. You are made of star stuff, looking back at the stars you came from, contemplating a return journey. And that, more than any technology, more than any discovery, more than any achievement, that is the most profound thing about being human. We are the universe waking up, looking around, and deciding to explore itself. Starshot is just the next step in that eternal journey. Thank you for taking this journey with me. If this video impacted you, if it changed how you think about humanity's future or your own place in the cosmos, please share it. Help spread the idea that this matters, that this is possible, that this is happening now. Like this video, subscribe to the channel, and most importantly, keep looking up, keep wondering, keep caring. The stars are waiting, and we're finally ready to answer their call.